Hi there, my name is Tariq, and today's tutorial I will explain to you the ADC Post Processing Block in Texas Instruments DSP. I'm using the C2000 Delfino MCU F28 379D Launchpad Development Kit. I'm gonna show you how to use the Post Processing Block to adjust a DC voltage offset. In this figure, you could remark that for every ADC, there are 4 post-processing blocks. Any post-processing block could be associated to any ADC result. ADC result 0 to ADC result 15 registers. Each post-processing block can simultaneously remove an offset associated to the ADC input channel, flag a zero crossing point, flag a high or low compare limit. Furthermore, the zero crossing and the compare flag can trip an event or generate an interrupt to the other peripherals. Using C code, I'm going to show you how to configure the ADC and any post-processing block to adjust an offset in Texas Instruments C28x DSP. Adjusting an offset means that I will subtract a value from the result conversion corresponding to the DC voltage that has been added. In this figure, actual ADC curve is the measured sensor voltage with DC offset, and the perfect curve is the ADC measured curve without offset. It is clear that the perfect curve is more correct to the ideal curve than the actual curve. Sometimes, sensor could provide us with voltage measurement image of the physical value with an offset voltage. This voltage could be corrected by soft if it is not corrected using the circuitry before feeding this signal to the ADC channel. This tutorial uses a timer zero interrupt. This interrupt service routine is an infinite loop of 15 microseconds. For this tutorial, I'm using ADCE and ADCB to demonstrate the conversion and adjustment of a measured input and subtract an offset of 200 points. I'm using timer zero code tutorial. A card will show up in the top right screen of the video. The timer zero interrupt will trigger ADCE and ADCB to convert SOC 0A and SOC 0B. The end of conversion of the ADC SOC 0 and ADCB SOC 0 will trigger an interrupt ENT1 for ADCE and ADCB. These two interrupts are totally independent. Interrupt 1 of both ADCE and ADCB will be used by soft to trigger the second SOC 1 for ADCE and SOC 1 for ADCB. When the end of conversion of ADCE and ADCB occurs, it is time to store results in ADCE results, ADCB results, and ADCE results offset adjust and ADCB result offset adjusted respectively. Each ADC could convert 16 SOC, and each SOC has its result register, and each result register could be related to any analog input. ADCE and ADCB will convert an input voltage ADC in A0 and ADCB to ADC channel A0 and ADCB channel B2 will fed by a voltage to the same potentiometer output. You could connect these analog inputs to any different source voltage between 0 to 3.3 volts. The voltage reference of the ADCE and the ADCB is 3 volt. This means every voltage over the reference voltage will be considered as 3 volt or 4095 points as result conversion. Now it's time to start working on the code. The code I am using is the same as the timer 0 tutorial code. In this code there is a file called manage_adc.c. In this file we have two functions. The first one is the configuration ADCA and ADCB. First, ADCA and ADCB set ADCA and ADCB to impulse position. In other words, interrupt will come after the end of conversion. Divide the system clock by 4, choosing 12-bit resolution for ADCE and ADCB. For ADCA, SOC0 will be triggered by timer and SOC1 will be triggered by soft. The same thing for ADCB. ADC channel definition for both ADCE and ADCB. And in the end of this function, power up ADCE and ADCB. The second function is to configure the post processing block. Choose post processing block 1 with SOC1 for ADCE. Choose post processing block SOC1 for ADCB. Load values of the offset. Load the value offset in the first register for ADCE and the post processing block for the second and ADCB. In the main function, I'll call the ADC configuration routine and I will call the ADC PPB post processing block configuration offset. In the main timer 0 function interrupt, I will wait for ADCE and ADCB to finish conversion of SOC0 for ADCE and SOC0 for ADCB. Force by software the SOC1 for ADCE and ADCB. And by the end, in the end, store result to the registers and variables. In the experiment part, I will show you how to debug this project. I will show you how to load the program, debug, and add variables to the watch expression window. So, to start, go to View and Target Configuration. When the window shows up, go to the Project menu and click Launch. Add variables to the watch expression by clicking Add to Watch Expression. Connect the CPU to the JTAG supplier. Load the program by clicking Run and Load Program. This project has been configured to compile Flash and RAM projects. You could either load a RAM or Flash version of the output file compilation. I will load a Flash configuration as you see here, but if you want to load a RAM configuration, click browse and go to the project profile, RAM, and click this and click OK. I will load a flash configuration, so I will cancel this and click OK. When the program is loaded to the CPU, to the DSP, click the green triangle or F8 to start the project. In the watch expression, you will remark that the ADC result is higher than the ADC result offset. In this example, I set the offset to 100 points. So, if you calculate the difference between the real value and the offset value, this is the same value as this. Now, I will change the potentiometer to show you the different voltage range for more clarifications. We reached the end of this tutorial. Please find all the relevant links in the description. I hope this video at least was interesting for you. If true, please consider supporting the channel by subscribing to my YouTube channel. Thank you for watching and see you next time.